It's accepting something. It's called an acceptor, right? Now, acceptors are then built on what we call finite automata, right? What is the difference between finite automata and automaton? Because you'll hear me saying that. So there's this automata, and then also these automaton. What is the difference? I remember you did this. I know you did this. Let me just check on my chat. Can people hear me? Everything is a bit dry. Yeah, I think they can hear me. They can hear me. They can hear me, right? So acceptors are built on this something that we call the finite automata, right? Automatas, finite automatas. And what is this? 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 And what is the difference between the two? Anyway, just to assist you, and because of the sake of time, right? So an automaton is just the singular, right? It's just one. Okay, one of these items you're talking about. Good. I see Newton has seen it. Yes. And then automata is just the plural, right? So there are many. So don't think like one is a different concept or is a different item compared to the other. Okay? So this is like a machine, right? It's a machine that we design. Okay, and this machine will have things like states. Okay, I know you remember that thing where you're drawing finite state machines. Actually, it's what we are talking about right now, right? Finite state machines where you are having different states like S0, S1, okay, something like that. And now you went between them based on a certain input, right? So you started somewhere and you went here because of a certain input, you went here because of a certain input. So this is what we are talking about, right? Anyway, just to condense everything, right? So we are just having this acceptor that is built on these finite automatons, right? Taking a certain string that you've written as lines of code, okay? Then using that, this acceptor is able to compare them with the language that you fed into this acceptor, right? So both of them. And then at the end here outside, you're told, yes, this string maybe belongs to this language, or no, it does not belong. Okay, it's similar to us maybe coming up with a certain mechanism, right, where we feed students. Okay, it's a bit crude, but try and see where I'm going, right? So we have this, it's like a machine, like the one that you find in airports or nowadays, security checks everywhere, okay, because of security reasons, right? And people are able to pass through them, right? So think of it that way. So people are passing through it, and then here you can be able to feed it a certain database, and the database maybe can say Strathmore students, SU students. Let me say that, right? So when a student passes, okay, depending on some certain things that you have in this database, right, they are either said to be SU students or no. Okay, so something like that. So we can say yes, they are students, or no, they are not. So that is like kind of like the bigger picture of what you're working with. I'll quickly shift to my notes. Okay, I don't see any question or concern. Let me just dive there. Oh, by the way, before I forget, attendance. I have so many people who are sending me emails about attendance. Okay, so you'll find that when you're beginning a semester, right, before you are, all of us, okay, are properly updated on the system. Okay, sometimes you'll find that you are said to be absent, especially if you join the AMS late, which can happen because of one or two reasons. Okay, so give it some time. Okay, if you have an issue with attendance, just note it down, and then maybe after a few classes, we are only at class 3, right? The third class, right? Maybe after like 6 or so classes, then they'll be able to start changing it. Okay, and then I can give you the correct attendance update. Anyway, so here, anyway, this is what I want us to talk about: finite automatons. Like we said, this one is singular. These ones are plural, right? So you can see what I'm drawing over here. So you can think of a certain string that you've written. For example, the one that we wrote the other time, a single line A plus something, and then you feed it to this acceptor, right? So that's the mechanism that we use to check whether a certain string belongs to a certain language. Okay. Then this acceptor is able to take it and compare it to this language, and then at the end, it's able to tell you yes, W belongs to a certain language, or no, it does not belong to that language. Now, these acceptors, okay, are then based on what we call finite automata. Right? Now, just to take you back, this is where now the theory of computation comes in, right? And automata theory, this is where it comes in, right? So if you remember, and if you've forgotten, I'll remind you, a finite automaton will consist of the following elements. It will consist of these several elements, right? It will consist of an input alphabet, right? It will consist of a set of states, the states like the ones that I was drawing, S0, S1, something like that. It will also consist of a start or initial state. It's obvious if there are states, there will be one that is going to start, On top of that, okay, there will be, okay, some accepting states. Okay. Now, one of those accepting states or even more can be final states. Okay. So you can also call them accepting states or final states because it can be something like this. And then maybe the last one here is the one which is the final. We often denote it with the double circles, right? The double circles that way, right? And then we'll have a start state, will always have an arrow. Okay. Just showing that it's uh, starting there. Anyway, we'll go through this. And then also a final item that it will have, the finite automaton, is a set of transitions, right? So a set of transition movements from one state to another, movement from one state to another, movement from one state to another. Now, I want to show you examples of these in the next slide and tell me whether they seem familiar to you. Look at something like this, okay? Uh, we are saying that finite automatons accept strings, okay, which we can follow a transition labeled with characters from a start state all the way to an accepting state. Okay, now this accepting state also can be the final state. Okay, you'll get to see what I mean as we proceed. But anyway, look at this first example that I have here. Okay, we are saying that this finite automaton over here is able to only accept one. Okay, so that is the only input it can accept. The only input it can accept is one. Okay, so that's the reason why if you try and feed 0 to this finite automaton, nothing will happen. You'll get an error, or what we call a phi, right? Often denoted as that. You'll get an error. It doesn't happen. Okay. Then the second one over here, this is another example, right? Just a random example. Okay. You can find this one that is saying, right? In fact, this one there should be an arrow here. We are saying that this second finite automaton, okay, accepts, okay, a number, any number of ones. You can even say an infinite number of ones. Okay, and then it's followed by a 0. Okay, how are we able to see that? We can see that this is the start state. I can also label it as S0, and this is maybe the final state, the accepting state as well, S1. Okay, so when you feed 1, right, you keep on just remaining on this initial state. You don't move. You just stay there. You just stay there. You just stay there. Okay? But then if you feed a 0, right, an input of 0, you're able to move from the initial state over here to the accepting state / the final state. I know these things are a bit familiar, but then let me just mention them. Then look at this final one, right? Which is able to accept A, the closure of B, and then A, right? So from the start state, which you can say this is S0, okay? This is S1, this is S2, okay? So if you feed A, right, you go from the initial state to one of the accepting state, which is S1. Okay. Now, if you feed A again, you go to the final state, which has the double circle. Okay. However, if you're at the second state over here, okay, the accepting state, and you feed B, right, you just keep on remaining at that location, that location, that location. I don't know. You've met these things before. I would like to hear someone acknowledge that. Yes or no? 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 Oh, good, 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 good. I like this. I like this. I like this. So I know I can't see your book. I know I can't see your book, right? But take your time. Try and design a very simple automata that just accepts this. On your book, a simple one that accepts this. That's number one. Design another one that accepts this. And then we'll talk a bit more about them. Something like that. And then maybe even the last one that accepts that. Try and design those ones. I'll give you 5 or more minutes. There are people who here are telling me they're having issues with their network. This is the opportunity. You can try and fix your network now. For the rest of us, just try and design finite automatons that are able to do that. The first one, the second one, the third one, right? And then we'll continue having the discussion. Great. I hope you're doing something. Okay. Now, just to remind you, maybe you forgotten your theory of computation previously where you met it, right? So when you are converting maybe like regular expressions, right, to FAs, in this case, in most cases, it's just a non-deterministic finite automatons. I'm going to explain what they are also. I'm just going to refresh everything. That's the reason why I said the class will be a bit short, but then I'm going to refresh everything. When you have something like this, right, concatenation of different variables as if they are these, right, what you do is that you create a state for each transition, right? So for instance, if you have A, you'll create one that moves from maybe A, so you'll have maybe you can use caps, one state over there to hold A, the first A is initial A here, okay? And then you'll create another one, maybe you can use capital letters B to denote the second one, transition for B, okay? And then after that, you can also have the last one now, which is going now to hold last transition for A. So this one may be your final one, so you can denote it with a double circle for that. Now this one is your initial, so you can draw an arrow that way. So yeah, you can have that. So just a hint. Okay. What about the second one? The second one. What have you done for the second one that is different? Somebody can say. I don't want to give the chance for people to share their screen. We may have a lot of confusion. So just try and explain what you've done, maybe on the chat. What have you done for the second one? What have you done to implement the second FA? Right, what is different? For those who are just joining us, right, we just picked up where we left. Okay, we just picked up where we left. We are trying now to try and find a way to create a mechanism that is able to test a certain string whether it belongs to a specific language that we have written our codes in. Okay, and for that we've said that we need something called an acceptor. Now an acceptor is built on the idea of finite automatas, right? So finite automatas, if you remember your computing theory, right, there are certain things there, here and there, right? So those are the things that we're actually looking at. We're just refreshing ourselves, and here we are just coming up with different FAs for different regular expressions. Good. So I can see everybody is at par, okay, which means we'll have a very easy time today, which also means we'll have a shorter class. We can rejoice and be happy anyway. So here for A, the first one, whichever you want to call it your initial state, you can call it number one, or you can call it capital A, right? So for this one, because this is A asterisk, so I hope all of you just put a loop, right? So it was just a loop so that you can have that, okay? So that is your A. You always have to label it. And then the second one, obviously, is that for B. You can just show that. So it goes there, right? My arrow there. And I have the final state. Sorry for the notation. Using that, anyway, that. So this is your B. I hope you've done that. The same also follows for the last one, right? So for the last one, so this one, the last one is the one that is going to have a loop, a loop. Now let me give you a last one that is a bit different. So what happens when I have A plus B, and then I have, yeah, let me even start with that. Then for those who are a bit faster, can try also this one, okay, something like that, and then maybe there's a closure of A. Okay. So when you're given something like that, what do you do? Okay. Rehearse and rehearse, rehearse, rehearse. Take your time. Okay. So what happens here? What happens here? One way to maybe remember, if you've forgotten, is to remember that this means A or B. Good. Perfect. Perfect, Hassan. Actually, just copy paste what you've said to everyone because I see the message is privately sent to me. Yes, but that is true, Hassan. Yes, yes. Believe in yourself. It is true, right? So what this means is A or B. It means that the initial state can accept either A or B, right? So that means when you're drawing it and you have your initial state, what has happened? Sorry. Okay, sorry. So that means if you're drawing your A, all right, your initial state, maybe my initial state in this case is capital A, or 1, right? Depends. Right? It means you can give both an A, which is going to help you transition from this initial state, right, to the accepting state. So maybe in this case, the accepting state is B, which also happens to be the final state. So B, right? So it can either accept A, a small a, or it can also accept B. So either will work. Okay. So in short, what I'm trying to give you is just a shortcut, right? If you remember, I don't know that you're given that shortcut. If you see a plus, right, most likely things will happen this way, right? There'll be something like this, kind of like two transitions from one state to the other. Then if you see concatenations where they are following each other, that means you'll have like different states, okay, to represent each movement. Okay, that's it, that's it, that's it. Then what about this one? What did you do for this one? The last one over here. This is a good one. Good. Okay. So after transition of A or B, the next state you will have a loop of A. Okay. So let me ask, am I correct in doing this or am I wrong? I would like to hear. Or question, is it that or is it this? Let me just analyze. If you have a question, just hold them because I haven't even begun speaking about them. I just wanted to see whether people at least have a basic understanding of what you're doing. Right. So we'll have that. Okay, so tell me whether it's option A or option B, right? So we have this. Okay. Then after that, we'll have something like C, and we'll have A here. I want to test something. So do you think it's 1 or it's 2? Which one is it? Which one is it? Which one is it? Okay, okay, okay. So here's the thing, right? You'll not be wrong in being confused, right? In saying that if A over here did not have a closure, it had A plus, right? A plus. That means you have to have at least one of the movements. Then we'll go with this. Okay. But now since we only have it's a closure, right? We have to consider okay an instance where in this case this one is an empty string. Okay, it's not existing, right? So it's just A and B. So option 1 is the correct one, right? But then with more examples and more practice, we'll be able to see this in more detail, right? So let me just finish the theory that I have, and then we'll do more practice, right? We'll do conversions of regular expressions to NFAs, and then later on we'll do NFAs to DFAs, right? So just allow me to finalize on the theory. Okay, but then if you have a very strong burning question, right, you can ask. I can give you like a few seconds just to ask. But then if you can hold it until we are done with the short theory I have, I would really appreciate that. Good, good. I see everybody is waiting. Okay. I also want to say that this movement that you're seeing over here, right, where the FAs are being represented in terms of the finite state machines, right, in terms of these circles in the different states, right. You can also represent this information, right, using transition tables. And actually, transition tables are very important when we are trying to convert between NFAs, right, non-deterministic finite automatons, right, to DFAs. Right? They're very important because using those tables, transition tables, right, we are able to identify some of those errors where you have an input, but then it doesn't cause anything to a certain state. Okay. Now, a deterministic finite automaton, right, should have transition for each input for every state you have. Right? I'll be able to explain that in more details when we get there, right? But what I'm trying to do is I'm just trying to introduce this concept of having transition tables representing this exact information, right? But now in a tabular notation. Okay. I'll show you an example. Okay? Consider this example that I have here, right? Consider this example I have over here, right? So I have this FA, right, that has 3 different states, right? The last one here, the accepting state, is also the final state, right? And what is the regular expression here? What is the regular expression here? By the way, that's another way where you're moving now from FAs to the regular expression. Let me see. What do you think is the regular expression here? Okay. What is the regular expression here? A few minutes. Going once, going twice. Ah, perfect, perfect, perfect. I have good students. Yes, so the regular expression here is A B, closure A, right? So you can see how easy these things are. Very easy, very easy, very easy. Okay, so you can represent this information also in this transition table, using transition table, right? It's represented the same information, okay, where we encode in finite automatons now, okay, automatas now using tables, right? And here you can see I'm giving a small key over here. Let me just move it a bit up. Right? I'm giving just a small key over here that says that the rows corresponds to the states, right? So these ones over here are the states, these ones here. Okay, if these labels here 0, 1, 2, those are the states, and that's how you'll always note it. If you're using transition tables to encode an FA, right? So the rows will represent the states, okay, the states, right? Then at the top, what we have the alphabets, right? These one up here, these up here, these up here, right? Those are your inputs, right? Those are your inputs. So in this case, you can see when I'm at state 0, and then I feed an A, where do I go to? I go to the first state, right? The first state. Right? Then if I'm at state 0 and then I put an input of B, I get an error, or what I was representing as 5, right? We can't use that one. Okay? That already tells you that this is an NFA, right? It's non-deterministic. Right off the curve, you should know that, right? Then if you're at state number 1, okay, this is accepting state, the first accepting state here. If you give an input of A, what happens, right? You go to 2, and that's the reason why you can see it's 2 over here. Okay? However, if you put B, right, you just keep on looping on that state. You'll not move anywhere, you just stay there. Then if you're at state number 2, which is the final state, if you put A, what happens? There's an error. If you put B, there's also an error. Okay, so that's another way of encoding FAs. Okay. Now, I'd like to start by talking about having identified those two. I'd like to start talking about these NFAs and DFAs. And I want to give us a few minutes to just share your thoughts. Okay? If you can activate your mic, even better. Okay? What do you remember from the theory of computation? Like we said, we are just rehearsing for this class, so that at least when we start talking about the codes and all that, we are not a bit blank, right? Anyway, so from your theory of computation and automata theory, what do you remember NFAs and DFAs were? What were they? And even better yet, if you want to go even further, you can start by checking what finite state machines are. Okay, you'll see that finite state machines, right, are split into two. There are those that have outputs. There are those that do not have outputs. Okay, so NFAs belongs to those ones which do not have outputs, and so does DFA. Okay, so this one there is no output, right? They are split into two major groups, right? No output. Right? Then on this other side, the ones with output, right? We have the likes of Moore and Mealy. I think my chart was not well drawn, but here you have Moore's diagrams. You can go and check what they are, and Mealy's, right? Okay. Also, here there is often a third one, okay, that is called epsilon NFA. Anyway, we'll not cover that one, so I don't think they need to mention them. Let's just cover these two. Anyway. So I'd like to hear your thoughts. You can write on the chat, or if you feel you remember something, you can activate your mic, which I would gladly appreciate using some points for you, so that you can remember what NFAs are, okay? And DFAs. Okay. Again, for those who are just joining us, as I give people a chance to say what NFAs and DFAs are, you're just trying to connect whatever we learned last week, regular expressions, right, with the mechanism that can help us identify whether certain strings that we've written in a certain programming language, if they belong to a certain language. So for instance, C or something like that. Right? And we said the thing that is going to help us there is something we call an acceptor. Now this acceptor is based on finite automata, right? And that is what we've been covering so far. So we've just been converting some regular expression, basic regular expressions to FAs. We've also seen that you can also encode an FA using a table, okay, what we call a transition table, where you can find that on the rows you'll have the states, and then on the columns you'll have the inputs. So in this case we have only two inputs, A and B, right? And you can see how we've encoded this entire FA over here using this transition table, right? Now from there we are now headed to these two. Yes, a tutti. I hope I've said it right. If not, tell me.
Yes, it's a tutti.
Good.
So a DFA,
Yes.
when a DFA takes an input of strings,
Yes.
it's either it accepts it or denies it at the end of the string. I mean, if you're given let's say a DFA, let's say you're given AB. Yeah.
Yes.
So in a DFA,
Yes.
if B ends in a finite state, I mean the final state, the
Yes.
string is accepted.
Okay.
And in NFA, if
Okay.
the B does not end in a finite state,
Okay.
still accepted, but it does not end at the final state.
Okay. Okay. That's one way of looking at it. Okay. Newton. Let me hear what you have to say.
Hear me?
I can't hear you. Is it my network?
Can you hear me now?
Yes, I can.
Okay. So for NFA, it has more than one acceptable state, while
Yes.
DFA, the only one.
Okay. So there is a sense of randomness, and everything is not determined actually. Good.
Yeah.
Good. Yes. The second person I see over there is Kevin. Kevin, say something.
Can you hear me?
Yes, I can.
Okay, so for NFA, I believe that for each input, there's some inputs during the NFA when you're drawing the diagram for the NFA. An input
Yes.
like, let's say, for example, A can follow different paths for the same input, but for DFA, one input can only follow one path.
Perfect. Good. Let me hear Isaac as the last person, then I can continue. Yes, Isaac.
Okay, so for DFA,
Yes.
now that you already said it's a finite automata with an output.
Yes.
So when given one current state and input, we normally know the next state.
Okay.
Then it only has one unique next state.
Yes.
And then there's no choices and there's no randomness.
Yes.
And it's the easiest to design.
Good.
While for a non-deterministic finite automata,
okay,
when you're given a current state, there could be multiple next states.
Yes.
These next states can be chosen at random.
Okay.
And all the next states may also be chosen in parallel.
I don't know whether everyone has had that one. That one is a very, very comprehensive explanation. Good. I like that. Let me go to the whiteboard. I always find the whiteboard to be better for me to explain, and I'm just going to give a very broad explanation for both. Okay, and then we can continue from there. Good. Let me hope I don't lose this because of network, right? So let's consider this. Consider I have this here. I have a, let me just take my time. I have B here. What else? I have C over here, right? And I have D over here. D over here will be the final state. Right? So consider this. So this A is actually my input state, and then probably I'm moving between these and this that way. I'm just going to have random. I can also move back here that way, right? I can also go up that way, and I can also go down here as well. I can also have this movement here, okay? And I can also have this one here. Then here I'm also going to have the same thing. So you can see it's very simple. It's not that complicated. Okay. And then after that, I'm going to have maybe here I'll have one. I can have one here. From A here I can have zero. Let me have zero here, and zero as well here. And then let me have one, and also have one here. And let me have zero and zero here. Okay. From the look of things, okay, what do you think that is? Is that a DFA or an NFA? From the look of things. Okay. Now, just to demystify everything that is out there that you maybe are thinking of, right? So this is a DFA. This right here is a DFA. Okay. And there are some things that I don't know whether they were mentioned, but there are certain things that we call them tuples, right? They are the 5 tuples that define finite automata, especially DFAs and NFAs, right? Of 5 elements, right? They're often denoted as Q, right? You'll also have these, right? The epsilon. You also have Q naught. You'll also have a set of final states, F. And then finally, you'll have what we call del. I'll explain what each and every one of them are. Okay. And using this, right, you'll be able to differentiate whether something or a certain diagram that you have is either an NFA or DFA, right? So Q in this case, okay, will represent a set of all states, right? So a set of all states. Right? Then you have this, okay, which will represent the inputs. For instance, in this case, what inputs do I have? You can be commenting on the chat. What inputs do I have in that diagram that you can see there? How many are they and what are they? Then Q naught, right, will represent the start, okay? Or in some cases, you can also call it initial state, right? Initial state, right? And then you'll have F, which will represent a set of final states. This is very important, right? So you can see a start state can only be one, but then the final state can be multiple, right? So they can be a set of final states. That is very important to mention. Then we have del, right, which now represents, right, the transition function. The transition function. Now, the best way to show the transition function actually to represent it is using the transition table. Okay, transition function, which for a DFA in this case is usually given by Q, which are the sets of all states, right, with the cross product of epsilon, right, which are the inputs, right, which should give you Q. I know, a bit complicated, a bit out there, but the definition will make more sense once we start seeing more examples. Now, what you'll find is both NFAs, okay, and DFAs, okay, will be defined by these tuples, right? The only difference is, right, so while this final one over here represents a DFA, right? For an NFA, this one will be given by this, and you'll see that there will be many, okay, 2 to the power of Q. Right? So that will be the only difference. Okay. But even better, right? The best way to see the differences between these is that, right, a DFA only has one unique next state. Okay, what does that mean? If you give it a certain input, for instance, when we are at state A, right, if you give a certain input 1 or 0, right, you don't have to wonder where you're going to move. Right? In this case, it's determined, right? Actually, the word deterministic finite automaton comes from that phrase or the term determinism, right? It's determined, right? In simple terms. So that means when you're at A and you put 0 or 1, right? The destination you're going to go, right, is only 1. Okay? But for NFA, it's a bit different, right? You may go to different places in random. Okay? And let me just draw also an NFA just to assist you compare the two. So that's a DFA. An NFA would look like this. This is an example of one, right? So consider this. You'll have something like A, okay, and then there'll be a sense of randomness, right? I'll move there for this. I'll call maybe this B, and then I can also move as well to this one here, C, okay, and I'll also move again here. To D, and then finally I can also even move here to another one, E. Let me explain, okay? And I can also even have a loop even as well. Okay, so here I can have this transition for 0, right? I can have 1 here, I can have 0, I can have 1, and even here I can also have epsilon. Okay, that is an empty string. Okay, so know this, right? So if you can look at this, right? I'm going to have this, I think this is in the notes, but then I want to explain first, right? You're going to find that the DFAs, right, only have one unique next state. Okay. Number 2, right? There are no choices or randomness. When I say choices or randomness, this is what I mean. Okay, so when you're at A here and I put an input of 1, where do I go? Okay, just take your time, right? Where do I go? I can either go to B or I can go to D, right? That is very different from this one here. When I'm at A and I put 1, an input of 1, okay, I can only go to this second state, which is B, right? If I put 0, I can only go to this only 1, okay? Don't be confused by the two ones which are here, right? So one is from B to A, the other one is from A to B. So the arrows are very important to show the direction, right? So that is very important. Okay? That is very different here, okay? Also, as you see, it's also quite simple to design from the looks of it, right? It's quite simple to design. And because of that, we can actually take now a DFA, okay, and code it, right? And code the DFA so that you can maybe scrutinize our work to give us a lexical analyzer, right? Now, the other hand, the NFA, right? The NFA is a bit different, right? So when you're given the current state, so in this case, my current state, you can say it's A, right? Okay. There are multiple next states, especially for each and every given input. So consider this, when I put 1 for A, I can either go to B or D, like I'm repeating before, right? Okay, so that means there is a sense of randomness, or you are like given a choice. You have to choose between one or the other. Are you going to go to this one or this one? Or you can even choose to go to both in parallel, right? You can either go to A and D at the same time. Okay. Also, something that you'll notice is, right, okay, in NFA, right, you can have an empty string or an empty input causing a transition, like this one here. This is epsilon. Okay, that cannot happen in DFAs. I'm seeing a lot of comments over here. Maybe I can go through them. Oh, good. So like everyone else, I see someone like the likes of Isaac, Papa, and so many other people here. So they've taken all these tuples, right, and highlighted them from this DFA I have here. So I don't know whether you can identify them. Can you identify the set of states? Can you identify Q for this DFA? Can you identify the inputs for this DFA? Can you identify the start and initial states? Can you identify the final states? Okay, and can you come up with a transition table for these here? Okay. I think that's a good start exercise. Okay. So forget about the NFA first. Okay. Just look at the DFA. Just look at the DFA over here and try and see whether you can identify all these elements. Okay. Okay. And especially this one, I'd like to see whether you've been able to come up with a transition table. I'll be able to draw it here as well. And then we can proceed. I like when everyone participates and we can talk about it. Okay. I want us to have a breather bit. Good. So I see some people are talking about the final state being D. That is good. So in this case, the final state is only 1, right? The set of all states in this case are A, B, C, D. This is very true. And then the summation sign, okay, over here in terms of the inputs are 0 or 1. Then the initial state in this case is A, which is denoted by this arrow over here. Okay. And then you have a state of final states. Again, we've said that is D. And then finally, we have transition function. So you can draw that using a table. It's okay if you're experiencing some network issues. I understand. Just remember to go through the work later on using the recordings. Okay. So I hope we are together. Hope we are together. So I hope on your book you've been able to identify Q, you've been able to identify this, you've been able to identify this, and this. Now, if you've been able to do that for the DFA, right, including coming up with a transition table so that you can get a little transition function, right? Try and do also the same for the NFA. I think I'll give us a bit of time, around 6 minutes, just to try and do that. In case you have a problem somewhere or you have a question, just ask, and I'll be able to answer. Remember, like I said, most of this class will be spent revising some of the things that you did before. Okay. I thought we'd skip it, but then I saw it's not fair to do that. Let's just rehearse and remember what we did, so that at least when we go to syntax analysis, we don't feel like there's a gap somewhere. So if you have a question, you can ask. I can see it on the chat. The rest of us, just try and find all these details, all these elements, all these 5 tuples over here in each and every one of these diagrams. If there is one that is a bit confusing, ask, and we can all tackle it together. Yeah, just to assist you, another one that maybe is a bit troublesome, especially for the DFA in this case here, is probably the transition table, so that you can be able to see the transition function, right? So I hope you came up with this. Actually, you don't have to draw all these. What you can do is, you can make it as simple as this. Actually, I'll have a box. Let me have a box. I'll have a box that way, and then I'll have just a middle line here, which I can also extend that way, right? And then I'll have at the top, like I said, are the inputs, right? I'll have 0 and I'll have 1, and then on the side here on the rows, I'll have the states now, okay, the set of the states. So I'll have A, I'll have B, I'll have B, I'll have C, and I'll have the final one, which is D. Right? Let me be a bit orderly. So I'll have a line there, a line there, and I'll have a line there as well. Okay. So it's just a matter of just you looking at your DFA over here and just decoding that information. So if you're at state A, right, the initial state, and you put 0, where do you go? Where do you go? You just go to C. Just go to C. So that is what you put here. We are just encoding now our DFA using a transition table. If I'm at A, I know you're doing this also as well. I'm just assisting maybe someone who is a bit confused somewhere. If I'm at A and then I have an input of 1, I go to B. Okay. Yes, maybe this one. This is B. This is B here. Okay. Okay. Then if I'm at B and I put 0, I'm at B, I put 0, I go to D. You can see that. Then if I'm at B, right, and I put an input of 1, where do I go? I go back to A. Okay. So there is nowhere where you're finding it's a bit random, or you have to choose between 2 different paths for the same input. Okay, so if I'm at this current state over here, which is C now, okay, and I put 0, where am I going to? I'm going to A, right? It's definitive, it's defined. If I'm at C, this is the current state, and I put 1, where do I go? C, I put 1, I go to D. Then I'm at D, right? And then I put 0, where do I go? I go back to B. Okay. Then if I'm at D and I put 1, I go to C. Okay. And there, my table is complete. Okay. I don't know that you've done for the same for this one here. And notice the difference. Okay. One more minute. And then I'll give us an official break, so that when we come back, we'll just finalize on maybe conversion between one NFA and a DFA. And then we'll hit the lab. With more practice questions to come, because maybe you've forgotten some concepts here and there, and questions are going to help us. Good. Okay, if you're having problems with the internet, Anita, I've seen that. It's noted. Okay. Good. Tanya, I've seen that. That is good. Yeah. That is good. Very good. Yeah. So for the NFA that I have here, it's also even very difficult to identify which is the initial state and the final state, right? You see, it wasn't even defined. But even if I define this as the initial state A, right, I can just pick one at random. Okay, I didn't identify Isaac, so it's okay if you feel a bit confused. Yeah. But I can just show that. I can show that one there. And I can even mention maybe something like this one is also the final state. But you see that the level at which they are random, right? That's the reason why I didn't have a final state. Let me not even have that final state, right? I just wanted to illustrate how you're finding different paths for the same input, right? Different paths for the same input. Good. I see people are saying they have the same results. This is good. I hope I've answered your question, Isaac. Okay. But then in later questions or maybe exercises, if you ever find them, the arrow that points to one state, this incoming arrow will always represent the input. Okay. And then the final state will always have those double circles. Okay. So that one will always be given. Okay, don't worry. For this case, these are special case. I just wanted to illustrate those unique attributes about NFAs. I'd like us to take a break. And while we are taking this break, okay, I want to challenge you. To do the following. When you come back, I'll still give you some few minutes to be able to do it, but I want you to have it during the break, so that in case someone is not that tired, they can be looking at it as we continue. Let me even use a text editor. That would be better. So convert the following regular expressions into the equivalent finite automatons, right? So I have number one. I have B, A, asterisk, B, okay, to A, B, I can put C, let me just better. Then I can have something like A, I can have C, and then this one I can put a closure there. Okay. Then now, make things a bit exciting, Let me see one which is a bit complicated, Yeah, this one is perfect. Okay, so that we can see that things are not always easy. Like that. We can put a closure there. We can have A, B, closure B. That's perfect. So we have something like that. Yeah, again, close that one. Let me just close that one there. That way. What else? Oh, by the way, you can also find that in some cases, I think I should have done that, right? In some cases, the plus can also be substituted for this vertical line. What do you call it? Does it have a specific name? So you can also see this regular expression defined as so. Still the same thing. Then you'll have a vertical bar that way. Get something like that. Okay, so these are vertical bar. So this one and this one are the same. Good. So our break, in case you have a question, just note it down. I'll be able to answer it. Right. So we can come back at 10:30. Okay. And I would like to start with the one by Moses. Moses says, please explain the transition function. Okay. I hope by now you're seeing that what you're trying to do in a way is like reverse engineer, okay, what our lexical analyzer is doing, okay, with the help of now the finite automatas, right? So that it can be able to check whether a certain string you've given it, right, belongs to a certain language that it has been set to, right? So the transition table, right, it's like an argument. Sorry, the transition function. It's an argument, right, that tells, okay, that tells this machine when you're given this state A, right? When you're given this state and you're given this input, right? What you do is that you'll go to C. Okay. Okay. So it's, let me look for simpler words there. Maybe that one does not okay. So consider this automaton that we have here. Let me start again. Automaton that we have here, right? Okay. So at any given instance, right, whether it's on the initial state or this current state, which is B at that time, or maybe this is the current state at that time, which is C, right? At any given time, right, if you have a state, right, and a set of input, which can either be 0 or 1 or even more, right? So this automaton, right, at this state will move to either D, A, or B, depending on the input that it has been given, right? The item or the argument that tells it to do that and where to go is what we are calling now the transition function, right? So the best way to illustrate it here in theory, when we are doing the automata theory, is usually using the transition table. We show using the transition table. But I hope in the back of your mind, you're seeing that maybe when you are coding this lexical analyzer, and maybe you're defining the automaton that you're going to be using, you may have to define a certain function that tells it when it is at a certain state, it has a certain input, it will transition to this different state. I don't know whether that makes sense, Moses, right? Have this in mind, right? That we are trying to understand the inner workings of our system in this case, which is the compiler, right? And the transition function, okay, is the argument that now tells that automaton where to go. Okay? So it's like the control of the driver. That's the reason why actually I see you've written there, because you're reading their set of all states and the inputs. Yes, yes. So you're dealing with the states and the inputs. So using that, you're then told where you're going to transition to. Okay. Moses haven't responded. I hope he's around. I hope I haven't given an explanation in vain. Oh, the other person has said it's okay. The question they had, they've been able to answer themselves. That is good. That is good. That is good. That is good. I hope you're back. If you're back, say something. Say something. And I hope you've been able to do this one. This one I know is easy. This one is easy. This one is also easy as well. Maybe the question is here. This is where probably you're having a problem. If you have, oh no. How many of us have been able to do the last one, number 4? Can you hear me or I'm disconnected? I don't know. Am I disconnected?
We can hear you.
Oh, good. Oh, you're just thinking and working. Okay. Okay. So the final one, number 4. I hope someone has been able to do something. Okay. However, for the sake of time, I'll be able to attach the answer on e-learning later on. Okay, for the sake of time, because I just want to cover something small and then give you the lab. So allow me to delete what I have over here. So I can cover something small about converting NFAs to DFAs. Okay. If you're around as well, maybe you can remind us, how are you converting NFAs to DFAs? I'm going to start with a very simple example, but then if you need more practice, I'll be able to upload more questions together with their answers so that we can save on time. And as we are doing so, right, it's very important to remember that the relationship between DFA and NFA is often condensed into a certain adage or phrase that says that every DFA is an NFA, but not vice versa. I don't know whether that makes sense. It's similar to the way people say every thumb is a finger, but not all fingers are thumbs. Yeah, I think that's the one, right? Yeah, so every DFA, right, is an NFA, right? But the reverse does not apply. However, you will have equivalent DFAs for every NFA. However, the first one is very important because it helps bring this, especially if you look at that transition function, right? Where we said this one, okay? You just look at the transition function and you look at so to give you this, okay, to give you other states, right? And this one having these to give you 2 to Q, okay? You'll see that this one is contained in here, right? So that is a very important part. Anyway, for the sake of time, let me have this. Okay. Good. If people recall the subset construction method, then I'm very happy. But then I want to show you a very simple way here. I have A, and then I'm moving to B using a very simple transition. I'm moving to B, and this one I may have 0. right? And then I can have this one being caused by 0 or 1. Okay. So this is my NFA. This is the final thing I'm doing, don't worry. Then we can start our lab. So I want us to go to DFA. One of the easiest way to do this is to do this, right? So just develop the transition table for this. Develop the transition table for this NFA. Okay. We are going to do this together. I hope you are doing the same. So I want to construct the transition table for this NFA. And then you let me know whether there are limitations to my method in case anyone finds them. Good. Then here I'll have A, right, and I'll have B. Here I'll have the input which is 0, and I'll have 1. Okay. So a question. So when I'm at A, I have an input of 0. An input of 0. Where do I go? I go to B. So this one I'll write very well B. Okay. Then when I'm at A, I put 1. Where do I go? So no movement. 5. Error. 5. Okay. So you can represent that using a 5. So when I'm at B and I put 0, I put 0. 0. Where do I go? Where do I go? B, I put 0. Where do I go? I go to B as well. Then when I'm at B and I put 1, I still go to B. B. So what do we need to do here? People say something on the chat. I feel like I'm alone. Say something. So what we need to do is we need to make sure that there are no errors here. We need to eliminate these errors that we have on our transition table. And what we do is that we create a new state or new states that we call dead states stroke trap states. Okay. Now the dead state and the trap state, right? Okay, will have transitions into them, right? But then nothing comes out. Okay, so we are calling it a trap state. Okay. So what that means is, right, I'm going to develop a similar table down here. Right, I'm going to have A and B. Okay, then I'm going to have my input 0 and 1. Right. So as before, this one is okay. Okay, there is a transition there, and also the good thing here is there is no randomness. Okay, so that is a question that we'll tackle later. I have B there. So where I have an error here for this input, right, I'm going to create a dead state which I'm calling to call C. Okay, so we are going to move to C, but then nothing will come out of C, so there is no transition, any transition from C to any other. Then for B, I'll still hold it, and B as well. Now, the story does not end there because you still have to include C on this section of the transition table so that you can show that their transitions for C, right, are based on C itself. So for C, you'll say that when you have 0, where are you going to move? You're going to move to C as well. So you're just going to create a loop there. And when you're at C and you have 1, you're just going to remain at C. Okay? So in this, we've created a very simple DFA for this NFA up here. So I'll start with this, and I'll show that this is my A. Okay. From there, I'll say that for me to move to B, which is still my final state. Okay. I'm going to have to input 0. And then at the top there, I'm going to have 0, 1. Right? But then remember, we created a new state over here, a dead trap state, which we are calling C. Okay, whose movement is caused by 1. But then also within it, right, there is a self loop that has 0, 1. Okay, so that's a very simple way of doing it. Now, I don't wish to go into the nitty gritties of optimizing DFAs. I'm assuming that was already done. Okay? Actually, I just wanted to refresh our minds on what we did before. Yes, there may be other methods that you can convert NFAs to DFAs. The one that I've given maybe may have limitations. I'm hoping someone will say some of those limitations. If they find, they can mention them, and I can give more examples, right? Yes, I'll give more examples, kindly because of time, because I realize if we do more examples, okay, for past rehearsal work, we may end up not being able to cover what is meant for a course, okay? So just allow me to do that because it was a refresher course for what we did in automata theory, right? Allow me to give you more examples on e-learning, okay? Well, detail them and steps and everything, and you can find them there. So at least you're not left behind in terms of course outline, course content, sorry, okay? I know it's a very basic example, but I'll give more. Also, I'm hoping you're going to revise your book on the theory of computation and automata theory. And in case you have more questions, now find other questions where you're trying to solve them and you're having issues, then there we can solve them together. With that being said, I would just like to show you something on the labs and how we are going to be doing them. Okay, so in my notes you'll find even detailed how to create even NFAs, right? Including maybe even some of the theories that are used, the algorithms that are there, some of the things that you covered in detail when you're talking about the automata theory. I've detailed them there. Okay? So in case you need more content there, you can always find it there. I want us to talk about this, the implementation labs and how you're going to be doing them. Okay? And here they are. So if you aren't listening before, maybe you are one of those people who prefers to go and listen to the recording later. This is a very important bit. Okay? So I want every one of us to create a folder. Okay? You can either have it in a local drive or in the cloud. It doesn't matter, right? Still the same thing. But then adhere to this when it comes to the naming. Okay, have the student ID and then underscore CC projects. Okay, short form for compiler construction projects. Okay, so student ID underscore CC projects. Now in that folder, each and every lab that I'll be giving you, okay, from time to time, I want you to save it there. Okay? Now there's a reason why I'm saying that, because I want us to train on two things. One, discipline, okay, self-discipline. And number two, ordering your work. Okay? So that at least we can have a sub-series and projects that are leading up to the final project. Okay. Also, I don't want if I keep on asking for you to submit more work, right? It will mean that you'll have more work, and like you guys said, you're in the final year, right? So it's better just to optimize the entire process. So I'm thinking, okay, create that folder, whether in your local drive or in the cloud, name it this way. Okay, and then save your labs in there using relevant names. So for today's lab, for instance, is lab 1. You can name it lab 1. Okay? But you can give more details, but have that keyword lab 1. Okay, and then you'll be saving your work there. After specific milestones, maybe after certain labs, right? I'll ask you to share that folder. Okay, on e-learning, or if I find e-learning maybe has limitation in terms of size, I may even create a unique email address for us that we can use to submit our work on Google Drive. Okay? And you can do that. Okay. Also, something that is very important, like I said, I'll not be teaching the basics of programming. Okay? So I'll be giving you tasks that you'll do. In case I find the task is a bit complex, I'll give you the hints. I'll give you, for instance, I'll tell you you'll have to create a loop, you'll have to create a function, something like that. Okay? But for today's lab, it's quite simple, right? You can even try and find some help online, but because it's a start, it's a very simple lab, right? I just want you to implement an ad hook, a very simple lexical analyzer. I want to see whether you can remember what we did last week. If you go through my notes, you'll find I have a simple code there. It's not complete, of how to create an ad hook, a lexical analyzer, okay, that is able just to take any string and then maybe say it's part of a certain item or not. Okay. Now you can either use C or C++, whichever you feel comfortable with. Okay. If there's any other language that maybe you feel you are better suited to use, you can, but then just ask in advance. Okay? Just request in advance. Just let me know so that I can check and see whether it's compatible with what I'm working with. Okay. Now that lab will be worth 6 points. 6 points. And then later on, we'll be able to reconsolidate them, and then we can get the total marks for our labs. Again, I'll not give you so many labs for you to submit. Okay? So don't fear that you'll be overwhelmed with a lot of work. Okay? Then also here, you'll always find that I'll always do this. I'll always give you a chance to get bonus points. So I'll have a bonus round over here. I'll not even say what this is. You can go and check on it. If you find it, you can implement it. If you do so, you'll get an additional 3 points. Okay, so this one is mandatory. This one is mandatory, a must do. But then if you do this one as well, and you save it in there, and I find it when I'm asking for it, maybe in a week or 2 weeks' time, when I see the milestone have been met, I'll give you an additional 3 points. Okay? That is good. There. Okay? I don't know whether there's a question on that lab. Okay? So there is no deadline, Vivian, like I said, right? So there's no deadline for you to submit. Okay? That's the reason why I said, right? You create a folder and then you'll do that work in there. Okay? That's why I'm saying I'm testing your self-discipline, right? I'm hoping you're going to do that lab this week, because next week again I'll have a smaller lab. Okay? That way. And then after a specific milestone, after some time, okay, I'll just ask for the work based on what you've done. So if you don't do the work each and every time you're given the work, it means when a deadline is given for you to submit the folder, okay, you'll work over time, having to work on maybe 2 or 3 different labs. So my advice is this: there is no official deadline, but if I were you, I would make sure that this lab I've done it by next week, and then saved it in that folder of yours, so that in case it's called upon, you'll be able to submit it. I think that will make our work easier. Again, like I said, we'll not do so many labs. We'll try and optimize the entire work. Any question on the lab? Cosmos, I see you asking whether we can use Python. Allow me to respond to that later. There's something I'm working with. Let me just check whether it's compatible with this. Okay. Cosmos, maybe you can remind me if you see I haven't given you a response by when? By tomorrow afternoon. Just reach out via email and I'll be able to respond. Okay. And anyone else who wishes to use a different language, okay, you can contact me via email and I'll be able to respond. Any other question? Okay. So key terms, just create a folder, cloud or local. This is better. If you can find somewhere you can save it on the cloud, it will be much better. Why? The story of my PC crashed should not be an excuse. Okay, that's the reason why you lost the folder. Okay? If you're asking on which notes, maybe you saw I had created the ad hoc lexical analyzer in these notes. Actually, they are already on e-learning, but then I'm going to update them because this final section is not there. So yes, so lecture 2, there should be somewhere where there is a simple one. Another question on the lab. Another question. But also the reason why I haven't given so many hints on how to create a simple lexical analyzer, I'm trying to see how you're going to interpret that question. Okay. I want to see what you're going to do. Are you going to create a function that maybe is going to be calling upon a certain string and then just examines it? Okay. Or are you just going to create loops that are just going to be assessing whatever input you give them? Okay. So that's all I'm just testing. Okay. So the question is open-ended. There is no specific way of doing it. I don't see any other question about the lab. Okay. There's another important question and concern I have over here for you. Okay. So at this section, if we are in class, in the physical classes, I would have announced that you have 2 weeks, and then after that we'll have a CAT1. Okay, because we've reached, if you go and look at the course outline, after lexical analyzer we are supposed to have CAT1. This is what I'm asking because of the conditions that we are in right now, right? I'm asking this for the class. Which one do you prefer, a CAT1 or an assignment? Okay. Keep this in mind. If it's a CAT, chances are it will be a takeaway CAT. So there will be no much difference. Okay. Maybe depending on the fact that one may be more application, the other one may be question testing us in terms of some of those, maybe solving questions, algebraic expressions and all that. Okay. So you can let me know. You can even start suggesting now as I give some points to some people who have spoken today. Okay. And also, let me say this, I appreciate those who have been sending emails. So many people have been sending emails talking about things that they found out about compiler construction. Others even sending mini papers that they've written. Okay. Do note I'm giving you points. Every time you do that, I'm always giving you points. Okay. So you guys can be having that discussion, and then I'll just come back very quickly. Let me just give some people today who have said something. Great. Yeah. So I see people are just some want CAT, one other ones want assignment. Can we have a poll? Yes. I think we can have a poll. Let me do this. I think this is better. No need to make a hasty decision. Huh? So consider this. Let me just repeat again for those maybe who didn't hear. Okay. Where is that? Where is that? Again, look at what is better for you guys, and then just decide. You can discuss in your groups, and then the class rep can reach out. So if it's the CAT one, the takeaway, I'm going to give a takeaway CAT, right? It will be more of solving questions, right? Solving questions, right? Okay. So probably it will be more objective, right? So there's an answer for it and all that. If it's an assignment, more open-ended questions, right? Maybe like 2, and then you'll have to answer, maybe even come up with a small code or something. Okay? Either way, you decide. So if we have a takeaway CAT 1 right now, then later on we can have an assignment, or we can start with an assignment and then later on a CAT 1. Okay. So you go guys discuss, and then the class rep, you can contact me tomorrow in the afternoon. And while you are doing that, you can also remind me to upload more questions for what you've done today, because I know it was more of a rehearsal of what you did before. Okay. So I'll upload more questions with more steps on how to do them. Okay. Good. So I hope that is okay. Julie, I see you've suggested we have a poll. I think that's better. So you guys can go and discuss, and then let me know by tomorrow. Same as anyone who wants to use a different language for the lab, for this lab. But then I would advise you to be more consistent, right? Be more consistent. If you're going to use one language, use that. If you're going to use like 2 languages, try and use 2 languages. Maybe it will give you more work, but then just choose one and then stick with it. Okay? I think that's okay. If there are no other questions, right? Anybody who wants to go and start working on the lab that I've given, yes, you have the permission to leave. Okay? I'll stick around for around 1 more minute, to see whether there is anyone who is going to ask a question, and then I'll also disappear. That being said, class rep, kindly remind me tomorrow what I've said, as well as your decision whether it's a CAT or an assignment that you wish to do. Okay. I see my chat is popping. I'll check. I don't think, like, I'm assuming I'm not going to disappear without answering your question. I'm just checking on something on my end before I go back to my chat. Just a second. Great. Oh yes, CATC. Okay. Moses is asking, I'm wondering if a lexical analyzer is implemented using C or Python, which one would be more efficient, or maybe the performance would be the same. That question may be a bit subjective, Moses. It may depend. It may depend on what you're trying to say. I don't know what structure you'll use in both instances for C and maybe for Python. Okay. Anybody who wishes to join in this discussion? This is a good question. What do you think would happen if you have a lexical analyzer that I'm assuming in this case Moses does the same thing, right? So you know, like I said, the example that I've given, the lab that I've given right now, right? So this is what we are calling an ad hoc lexical analyzer, right? So it's not generalizable. So you'll find that you'll have many mistakes here and there. It will not even be have errors. For instance, when you have key terms and keywords, it may have those confusions. So I'm expecting that is what you're going to build. Okay, the second one, which I'm calling an automatic lexical analyzer, which applies flex, that is the one that maybe you'll find that may be applied out there. Okay? So this one, okay, I understand when you're asking now, when you use C or Python, right, what will happen here? Because you remember, when we are building this, we said that we use, we just build a pacer, right, all together using certain tools that is able to work with any of those languages out there. Okay? But now for the one that we've just built over here, which is just a simple, just an ungeneralizable case. Okay? So when you ask, when you use C in Python, which one is better? I think it will depend on the structure that you have. Okay? So you may find that maybe on one side you may have some redundant elements, okay, that will force the performance to be a bit low. Okay? But then I'm thinking if the structure is the same, okay, by structure I mean you've used similar functions, maybe the loops and all that, I don't see why the performance will be different. Okay? Or maybe a better question you're asking is between C and Python, which one is more efficient? I think that is what you're asking. I don't wish to deny you the adventure of learning why Python was invented and who came up with Python. Okay? There's a story I was once told that the guy who came up with Python was just tired of writing the header files and all that. He just wanted a simple language that he can write whatever he needs and then it's applied. Now, whether that translated to better performance, how about you tell me? Just go and check and then let me know. I hope Moses, you are there. There's also someone who had asked a question previously. I answered, but they never responded whether they got the answer or they're okay. I'm going to assume the silence means they're okay. Oh, good, Moses. Okay. So let me know. I think the question that maybe you're driving towards is asking whether C or Python, which one is more efficient? Because if the structures are the same, okay, you followed a common structure, right? I do believe it should be the same. Okay? But then performance also depends on a lot of variables. Okay? You'll find maybe, for instance, in one language, you can write something more efficiently as compared to another, right? It's more convenient to write it in one language as compared to another. But then the question I'm asking is, does that translate to better performance? Okay. Good. In case of any other questions, I want to give you a whole hour to do that, so that someone does not say that they didn't have time to do the lab. Let's meet next week. If you have a question, just drop me an email. I'll be able to respond immediately within the next 1 hour. Have a great week.